Greetings. Today we're going to look at generating pitches based on MIDI note numbers. We will also look at using the pitch utility classes to choose pitches based on common scales. We will also look at creating our own scales. Finally, we will use an accelerometer to move up and down through some different scales. Before we look at using HappyBrackets to generate our pitches, let's have a very brief look at what MIDI notes are. MIDI is a communications protocol standard used by many musical instrument manufacturers to communicate between devices made by different manufacturers. An instrument from one manufacturer, for example Roland, can send instructions to an instrument from another, for example Korg. One of the message types used to communicate is the note on message. This is where a controller device, such as a MIDI keyboard, sends a message to a MIDI sound engine, such as an external synthesizer or the onboard MIDI playback on your computer, that it needs to play a particular note. Whereas in standard music manuscript, a composer indicates the note to play by drawing a note head on the staff. MIDI, however, uses a number to define what note to play. To play the note a semitone higher, we send a message with the note number 1 higher. Likewise, a sound a semitone lower is one number less. This means it is very easy to use mathematical equations to dictate what notes you want played. For example, adding 12 to a note number plays the note 1 octave higher. Adding 3 raises a note by a minor third. Subtracting 5 lowers a note by a perfect fourth. Let us create a new composition so we can explore some of the capabilities we have with HappyBrackets using the pitch class with MIDI note numbers. First, create a new composition by right-clicking the source folder. Click New Java Class. For the kind, select HappyBrackets Sketch. We will give this composition the name My Pitch Generator. Middle C is note number 60. Let us define that right now. Let's create our basic wave player by typing basic wave player. Remember to allow IntelliJ's auto suggestion feature to enable you to write the code with greater accuracy and speed. Instead of an initial frequency of 1 kHz, we want our initial frequency to be that of middle C. We're going to use the function pitch MTOF, which means MIDI to frequency. So if we put a MIDI number in here, we will return the frequency of that note. Enter the default value for the volume by pressing enter. Let's also change the waveform type from sine wave to square wave. That just makes the definition of pitch changes a bit easier to hear. Let's compile and run. You can hear a square wave whose frequency is that of middle C. Okay, let's play a 2-octave chromatic scale starting at a perfect fifth below middle C. To do this, we need to define our maximum and minimum MIDI note numbers. We said our minimum would be a perfect fifth below middle C. A perfect fifth is 7 semitones, so we will have middle C minus 7. We said we wanted a 2-octave scale, so we will define our maximum as 2 octaves above our minimum. We need some sort of counter to make our notes scale. Make sure you add the variable above the word override because it needs to be a class variable. We're also going to need a clock to regularly increment the note we're going to play. Type clock timer to generate our clock. Change the default to 300 and press enter. Each time the clock performs a beat, we want to play the next note, so we will increment our counter. We need to define our MIDI note as the minimum note value plus the note counter. We also need to check that our note is within our defined range. If it is not, we will use our minimum note. We need to convert our MIDI note number to a frequency. Now set the audio frequency object to this frequency. Now run your code. You can hear a repetitive 2-octave chromatic scale starting at F below middle C. Press stop. We can easily make symmetrical scales by using simple mathematics. For example, you can make a whole tone scale by adding 2 to the number on each iteration, or a diminished 7th arpeggio by adding 3, or an augmented arpeggio by adding 4, or a cycle of fourths by adding 5. Performing a major scale is not so simple mathematically because the distances between each degree of the scale are not identical. HappyBrackets has a utility class to enable you to easily get the correct distance based on the scale degree. To obtain a major third, you can use the third element of the pitch major array. You'll notice that the number for a third is 2. In standard Western music, we count the starting note as 1. E.g., to count a third above C, we go C, D, E. In the computer world, however, numbers count 0 as the first index in an array. Let's change our counter back so it steps by 1. We can get our scale degree by using a note counter as the index to the pitch major array. Now just add this scale degree to our minimum note number. Let's see what happens if we run the code. You'll notice that when our counter gets to 7, which would have been our octave, we get an array out of bounds error. This is because there are only 7 different numbers in the array, and so we can only select from indexes 0 to 6. When we tried to access index 7, we got an out of bounds error. To get the scale degree of the note without getting an exception, we will need to use a modulo function, which basically gives the remainder of a divide. For example, if it's 11 o'clock and we add 2 hours, we get the number 13. We perform 13 modulo 12, we get a result of 1, which would be 1 o'clock. So 11 o'clock plus 2 hours equals 1 o'clock. If our note counter was at 10, the note we want is an octave plus a perfect fourth. To get the scale degree, we get 10 modulo the array length, which is 7, which gives us a value of 3. If we look at index 3 in our major array, it gives us a value of 5, which is a perfect fourth. Our octave will be the note counter divided by the length of the major array as an integer, which gives us 1. We need to multiply this octave by 12 to get the number of semitones we need to add to our scale degree. So our final MIDI note will be our minimum note plus our scale degree plus our octave times 12. You can change the type of scale to minor, Dorian, pentatonic, cycle of fifths, or you can make your own custom scale. You'll notice that if we want to change the type of scale, then we need to change pitch major in each equation that uses it. We can make this a lot simpler by defining our scale as a variable and then using this variable in place of pitch major. We can easily change to pentatonic just by changing the value of current scale. If you look at the example in MIDI scales custom scale, you see how we created a custom diminished scale by defining our own array of integers and indexing it as we would the utility version from the pitch class. Okay, let's have some fun. Let's add an accelerometer and make it so that we generate notes from the major scale, which change with the x-axis. However, if we turn our device upside down, we will play notes from the pentatonic scale. Let's remove our limiters and remove the incrementing of our note index. Below the end clock timer line, add an accelerometer by typing accelerometer sensor. If our z-axis is less than 0, use the pentatonic scale. Otherwise, use major. We'll scale the accelerometer x value, which is -1 to +1, and convert it to a range from 0 to 7, which will give us an octave over our pitch array. We'll do this with the function sensor scale value. The first two parameters are the normal minimum and maximum values for the sensor. The next two parameters are what you want the minimum and maximum values to be, while the last parameter is the current accelerometer value. Scaled x will be a value ranging from 0, pointing down, to 7, pointing up. Now assign this value to our note counter. Let's simulate what's going to happen. Changing the x-axis slider simulates tilting the device, which will select the required note in the selected scale. Changing our z-axis will simulate turning the device over. Okay, let's try it out on our actual device. So that's it. We saw how to convert MIDI note numbers to frequencies. We also saw how we can use the pitch utility class to generate different types of scales, how we can make our own scales, and how we can easily switch between them. Finally, we played notes from a scale based on accelerometer values.